The purpose of this video is to introduce the topic of partial derivatives and then show how partial derivatives are used in propagating uncertainty in the context of this physics lab. So dealing with partial derivatives is not something that is part of a prerequisite for this course, although some people in the class will have seen this, but others have not. So that's why we want to take a little bit of time to go over this. So this initial part of the video deals with basically an introduction to partial derivatives. So to start with, let's say we're given a function y equals 4x cubed. And let's say that I want to take a derivative of this. I would write that as dy dx, and that would equal 12x squared. Let's say instead that we had a function that looked like this. I'm going to change symbols. So we'll say the function f is going to equal 4x cubed times y squared. So this function is a function of two variables, whereas this function over here, actually sometimes we would write this as f of x, is a function of one variable. So I could write this as f of x and y. So if I want to take a derivative now, the question is, well, I have two variables, so what do I take a derivative with respect to? I can take it with respect to x or with respect to y, and that's where the topic of a partial derivative comes into play. So instead of writing the letter d for derivative, we write a kind of a slightly different looking symbol, and it's kind of a curled over d that looks like that. So I'm going to say that's the partial of f with respect to x. And we can also talk about the partial of f with respect to y. So again, because this is a function of two variables, x and y, we can actually write two different partial derivatives. So the rule is that when you want to take a partial derivative with respect to one of the variables, you treat all the other variables as constants. So for example, if I can rewrite the function as, for example, 4y squared times x cubed. Or I can write it as it is up there as 4x cubed y squared. So those are the same functions, right? Just sort of moving things around. And the idea is in the first case, this 4y squared, I'm going to treat that as a constant. And I'm treating that as a constant because I'm taking the derivative or the partial derivative with respect to x. And in the second case, when I want to take the partial derivative with respect to y, I'm going to treat the 4x cubed as a constant. So once you make that step, once you separate what's constant versus what is variable, completing the partial derivative is now just like a regular derivative. So if I'm taking the derivative of f with respect to x, or the partial of f with respect to x, I have my constant term. So I'll just rewrite the constant just like you do with a standard derivative. So that's 4y squared. And then I have to take the derivative of x cubed with respect to x. So that would be 3x squared is that derivative. And so then I can just multiply through. 4 times 3 is 12. And I usually regroup in the same order. So x squared, y squared. So that would be the partial derivative of f with respect to x. For the partial derivative of f with respect to y, I treat the part 4x cubed as a constant. I then take the derivative of y squared with respect to y, and that is 2 times y. And then that gives me 8x cubed y. So that is an example of taking two partial derivatives of a function of two variables. So section 3.8 of your lab manual deals with the topic of propagation of uncertainty. So I'm going to cover that material now. The idea is we're going to start with something generic, and then we can talk about a specific example. So in a more generic case, you could imagine that we have a number of variables. So let's say we'll call all the variables x. So let's say we have x1, and x1 is going to equal some best value, so an x1 best, and plus or minus some uncertainty for x1. I'll just call that u1. And we could also have another variable, x2. So it would equal x2 best plus or minus some uncertainty. And we could have another variable, x3. In fact, we could have, in principle, as many variables as there are. It doesn't really matter. So, etc. There, it's supposed to be an etc. You can imagine, these are things you measure in an experiment. And if you have an equation that you're trying to apply them to, say that whatever the thing is that we're trying to apply these two to solve for, we're going to say that that is going to be f, whatever f is. And f is a function of all of these variables. So x1, x2, x3, dot, dot, dot. And the idea is that f itself has a best value plus or minus some uncertainty. And so really the question is this: if you have all of these variables that go into a function, and each variable has its own uncertainty, how do you determine the final uncertainty associated with how those variables are combined into a final function? So that's really what we mean by propagation of uncertainty. So we are propagating the uncertainty from each of the variables through the function into a final value that is the uncertainty of that variable itself. So this is really what we're trying to solve for. Now it turns out, so before we get to the uncertainty, we'll talk about this f best. The f best part is the kind of the more straightforward part. So f best is just equal to the function evaluated at all of the best values. So this is kind of a pain to write out, but maybe I'll just write the first two. So in other words, the best value for f is just you take the function, whatever it is, and then you plug in each of the best values for all of the x's, and then you're done. Okay, that's the first part. Now the second part is how do you determine the uncertainty? So I'm going to write a long equation out here. So the uncertainty is going to involve the square root of a big term. And I don't know how long I have to make this line go, so I'll just go to there for now. What we do is we're going to multiply the squares of a number of values, and then we're going to add them together and then take the square root of everything that we get. Each one of these products is associated with one of the variables. So let's say that's associated with the x1 variable, that one's associated with the x2 variable, that one's associated with the x3 variable, and then dot, 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 because who knows how many variables there are. So for every variable, you're going to have one of these products, and each product involves the square of two things. The first part, and this is where the partial derivative comes in, is we have to take the partial derivative of the function with respect to that particular variable of interest. So partial of f with respect to x1. In this term, it's going to be the partial of f with respect to x2, and the partial of f with respect to x3. So you take the partial derivative and you square it, and then we multiply by each of the corresponding uncertainties squared. So u1, u2, u3, quantity squared. And this is going to give a number, and that number is going to be the uncertainty for f. So now we'll look at an example. Now we're going to work through an example of propagating uncertainty. And in this example, we have a sphere of radius r, and we have determined the mass of that sphere. So the radius with uncertainty is 2.2 plus or minus 0.1 centimeters, and its mass is 359.6 plus or minus 0.4 grams. So we're trying to solve for the density, so rho, and rho is going to be determined by a best value plus or minus the uncertainty in rho. So we'll start with calculating the best value. So the best value is simply going to be whatever the function is, and we're going to then plug in the best values of r and m. So we need to determine what is this function. Well, the density is the mass divided by the volume. So this would be the mass divided by a volume of a sphere, which is 4/3 pi r cubed. So we could write that as 3m over 4 pi r cubed. To get the best value, we take that function, and we're just going to plug in the values, the best values we have for the variables. So the best value for r is 2.2 centimeters, and that is cubed. And the best value for the mass is 359.6 grams. And so if I put that in my calculator, I get 8.06, and I want to write more digits here because we're going to use the uncertainty that we calculate to actually tell us how many sig figs. So I'm going to throw in a couple extras. 2, 3, 8. And that is grams per cubic centimeter. So this is the first part of the process to calculate rho, or the density. So now we have to focus on calculating the uncertainty. So maybe I could call this part up here that we just did step 1, and now we're going to work on step 2. So step 2 is to find the uncertainty. So the uncertainty in rho is going to be the square root of the partial of the function of rho with respect to one of the variables, let's say m, squared, times the uncertainty in m squared, plus the partial of rho with respect to r, the second variable, squared, times the uncertainty in r squared. Now we need to find these partial derivatives. So the partial of rho with respect to m. Well, we look at our function here for rho, and it's 3m over 4 pi r cubed. Well, m is what our variable is, so 3 over 4 pi r cubed is constant. So we'll pull all those out in front. So I'll put 4 pi r cubed and a big 3 in the numerator. That's the constant. Then we take the derivative of m with respect to m, and that is just the number 1. And so we are left with 3 over 4 pi r cubed. And we can plug numbers in for that. We would get 4 pi. So the radius is 2.2 centimeters cubed, 3 in the numerator. So plug that in the calculator, and I get 0.02242 and the units for that are 1 over centimeters cubed. So we do the same thing for d rho dr. So I go back to the definition of this function. Everything that's not an r is considered a constant, so 3m over 4 pi is constant, so I'll pull those out in the front. 3m over 4 pi, and then I have to take the derivative of 1 over r cubed. So I'm going to do this. I'm going to say, what's the derivative with respect to r? I'm just kind of writing this as a separate step of, instead of writing it as 1 over r cubed, I'll write it as r to the minus 3. And the derivative of r to the minus 3 is going to be minus 3r to the minus 4. So what that means is this is going to be, we'll pull out a negative 3, pull the negative 3 down, so the negative 3 times the 3 is going to be a negative 9 times m divided by 4 pi, and then this is going to end up with an r to the minus 4. So r to the minus 4 is the same as over r to the 4th power. So minus 9m over 4 pi r to the 4th. If we want to plug in numbers for that, which is helpful, so we have a 4 pi 2.2 centimeters to the 4th, and we have a negative 9 times 3, 59.6 grams in the numerator. So I'll plug that into the calculator, and I end up with negative 10.994, and the units for that are going to be grams per centimeter to the 4th power. It's very common to come up with unusual units here, as you see, because what's going to happen is we're going to be squaring this and then multiplying it by the square of the uncertainties. And in the end, we should end up with the units for density, because that is what the uncertainty should give us. It should have the same units as the original function itself. We're still working on step 2, but I've rearranged this page slightly. So I've written our original terms, r and m, up here with their uncertainties. We have our best value for density, our partial derivatives when we've plugged in numbers, and then our equation for the uncertainty as well. Now I'm going to actually apply this equation. So I'm going to say that the uncertainty in rho is going to be the square root of, we'll see how long that needs to be. We'll take the first term, d rho dm, and that is 0.02242. That has units of 1 over centimeters cubed. That whole thing is squared, and it's going to be multiplied by the uncertainty in m, which is 0.4 grams, and that term is also squared. And then we repeat this, so now we have to add the second partial derivative, which is negative 10.994 grams per centimeter to the 4th power squared, times the uncertainty in r, which is 0.1 centimeters, and that's squared. And we do the square root of the whole thing. If we look at the units here, the units on both sides should give us the same thing. So this should have units of grams squared divided by centimeters to the 6th. And this is going to be grams squared divided by centimeters to the 8th. But it's multiplied times centimeters squared. So that gives us grams squared divided by centimeters to the 6th. And that's good because when we take the square root of that, so if I take the square root of grams squared divided by centimeters to the 6th, that gives me units of grams per cubic centimeter. So the units work out as they are shown. So I'll just write grams per centimeters cubed out here, because those are the final units for that whole quantity after we take the square root. So now I'll plug some of these numbers in the calculator, and I'll do a couple steps here. So I'll start with 0.0000 804 plus 1.20868. Square root of that is grams per cubic centimeter. And plugging this into the calculator gives a value of 1.099 grams per cubic centimeter. Now we have our two rules for uncertainty. The first rule of uncertainty says that there can be only one sig fig. So what that means is the uncertainty for us is actually 1. The second rule of uncertainty says whatever the smallest digit is in uncertainty, that determines the smallest digit in your best value. And that means that our best value has to be in the ones place. So it's going to equal 8. And so our final answer for this question would be 8 plus or minus 1 grams per cubic centimeter.